So, having completed the first section of this 7th chapter, we now start solving the exercises. Now, if you recall, we had some problems, some minor problems with the definition of a finite series, that is definition 7.1.1. And now, back then, we said that when we solve the exercises, we are going to address these issues. So, now is the time. So, the first one is a made up one, I made this up, a justify exercise. We have to justify this definition rigorously using theorem 2116, which, if you recall, this theorem is the one which allows you to have recursive definitions. So, let's see what we can do to justify our definition of a finite series that we have seen in the text. And for that, let us recall the actual definition 7.1.1 so that we can see what are the things that went wrong there. So, the precise definition was like this. We started with two integers, b integers, and we had one finite sequence of real numbers, and let ai, where I varies from m to n, be a finite sequence of real numbers. In fact, the author said, the author elaborated on this, what it means for this object to be a finite sequence of real numbers. It just simply means that for every integer I lying in this range, there exists a uniquely assigned real number ai, a suffix I. That's what this means. So that part, of course, I am not going to write. Then we can define the finite series summation ai, where I varies from m through n. Recursively as follows. So after that, we gave one recursive definition. According to that definition, this symbol is defined to be equal to 0 if n is strictly less than m, and the other part of this definition is truly the recursive part, which says that the summation of ai as I varies from m to n plus 1 is recursively defined to be equal to the previous summation, if you want to call it that, where I varies from m to n plus a n plus 1, and these recursive relations are true if n is greater than or equal to m minus 1. This was our definition of a finite series in the text. Now the issues that we came across are like this. The first thing is that you can see that we have n plus 1 here. Okay, now I is varying from m to n plus 1. That means you can take the value I equal to n plus 1, and in fact you see this term here. For the value of I, that is n plus 1, the ai term is a n plus 1. However, this a n plus 1, if you truly look at the entire definition, it is coming from where? It is supposed to come from that finite series. However, here there is no a n plus 1. So that is one problem. Another problem is, we are not just simply, whenever we are defining things recursively, we are not just simply in an informal manner providing ourselves with a recursive definition which looks recursive simply because there is an nth stage and an n plus 1 stage, but we in fact have a precise theorem for that. So we should be, in any situation where we are defining things recursively, we should be able to do that rigorously using this theorem. So we have to address these issues. Now you remember these two things, okay, because now that we are going to give another definition which is also like this definition, but it will be slightly different. That is also a definition of the of finite series, but that will be rigorously defined using theorem 2.1.16. And the reason I ask you to remember these equations, it's because we are then going to see that in that modified definition also these things are true. So actually we end up having a definition of finite series themselves, but that definition will be rigorous. Okay, now because we are going to use theorem 2.1.16, that necessitates recalling the theorem itself. However, we are not actually going to use theorem 2.1.16 itself, but rather a slightly more general statement than this theorem. So let's recall that general statement. The thing we did in the section 3.5, which if you recall deals with Cartesian products, there we came across one exercise which is this. The solution to exercise 3.5, is it 12? Yes. Ends with a statement like this. Let A be a non-empty set and let C be any element in A. and now there is a function f from the Cartesian product of the set of natural numbers and a into a be a function, then there exists a unique function a from the set of natural numbers into a that satisfies these things, such that the value of a at the natural number 0 is this chosen element C, and the value of a at the successor of the natural number n is equal to f of n comma a of n for all natural numbers n. Do you remember this thing? This is where we started everything with the successor function, which tells us that every natural number has a next one, and in fact it later turned out that this n plus plus, after defining addition, it turned out to be equal to just n plus 1. So that's what it is. Now that we have addition and everything, now if you want you can just simply write n plus 1 at that stage when we were proving this thing. And in fact, okay, now this statement was simply mentioned at the end of the solution to this exercise. However, whatever we went through in that solution, that made it clear that this general statement is also true. In fact, in the solution actually we had, I think, in place of a, the set of natural numbers itself. Okay. Here, however, after going through that solution, we realized that if you replace that n here by just a non-empty set a, any non-empty set, a similar solution will work and will prove this statement. So this is what we are going to use here. Now, how exactly are we going to possibly use this thing to define a finite series? Let us see. So what we do is this. We start off just like what we have in the text. Let m and n be integers. Okay, do we need to actually start off like this, or no? In fact, there is no need to do that. There is no need to mention m. Let m be an integer and ai, we are going to define finite series, so we would need those ai's, those real numbers, but this time we are not going to consider a finite sequence, but we are going to consider an infinite sequence, or what we normally call a sequence of real numbers, with which we are more familiar. We have developed an entire theory of real sequences. So this sequence index I starts from that integer m, and it of course goes on be a sequence of real numbers. Now what we are going to do, we are going to define a function like this. And in place of a, now we are going to take the set of real numbers. And that function is this. Into the set of real numbers by this formula. N is coming from n, so our small n is a natural number and small r is a real number. The definition of this is r plus a n plus m minus 1. Okay. Now we have to see one thing carefully. Oh, this is not minus 1, okay, well, that's what I was thinking. This is plus 1. Is there something wrong with this definition? Let us see. That is what I am trying to see here is whether this f is a well-defined function. You take any element from this Cartesian product, it looks like this ordered pair, where n is any natural number and r is any real number. Okay. Now because n is any natural number, n plus m plus 1 is what? What type of number is this suffix n plus m plus 1? M is an integer. So n plus m plus 1 is also going to be an integer, but not just any integer. Because n is a natural number, n is greater than or equal to 0. So that means n plus m plus 1 is greater than or equal to m. In fact, actually it is strictly greater than m because we have plus 1 here. So that means this n plus m plus 1 is an integer greater than m. And that is why such AIs we already have in this sequence. So this a n plus m plus 1 is a well-defined term coming from this sequence. It is a real number. And it is unique, of course, because the sequence itself is a well-defined function from the set of natural numbers to the set of real numbers. So for given n and r, this a n plus m plus 1 is a unique real number, and it does not, of course, depend on r. And r then again is a unique real number because it's given. So their sum is a unique real number. So that means for any element, this ordered pair n comma r coming from the domain, we have an element with which we are associating this ordered pair that is a real number and that is unique. So that is why f is a well-defined function. Okay. So now if we apply this thing, so what are we going to write? Hence, by the remark at the end of the solution, to this exercise 3.5.12, there exists a unique function A, which let's just give it another name, G, from N into A, for us from N into R, such that these things will be true. G of 0 will be our chosen element from A, that is that means in our case from R, but we haven't chosen anything. Now we will choose such that G of 0 is this AM. So the C that you see here, we can of course choose that C to be the first term of this series, this sequence AM, and it's a real number because this is a sequence of real numbers. So I am choosing this C from R, which plays the role of capital A, and these recursive relations are true, and they translate into this. Translate means we are just simply going to write this thing. G of n plus 1 is equal to f of n comma gn, g of n, for all n belonging to n. Okay. So this is just simply an application of this remark to this current situation. So far we don't see any series or anything, and now it will come. We then define now the definition will come. Define our finite series. Like before, AI, where I varies from m to n. Okay, to be equal to, it's partly defined. It is defined to be equal to g of n minus m if n is greater than or equal to m, and it is defined to be equal to 0 if n is strictly less than m. Now this second part of the definition already matches with whatever we previously had in our original definition 711. That is because if this upper integer n is strictly less than the lower integer m, where things are starting, then the series is defined to have the sum 0. This part, however, does not look familiar. So we now have to see that we in fact have actually got the previous definition minus all the possible inconsistencies that we previously had. So we can see the following. So the only thing now we have to see is this. That this thing turns out to be equal to this plus an plus 1 if n is greater than or equal to m minus 1, because that's what the original definition says. Now if we can show that this is also just like what we had previously in the original definition, then that means our new definition matches with the original definition, because these are the only two possibilities. Now when n is less than m, then this is equal to 0, which matches with what we had previously. Now if n is greater than or equal to m, then we have to see that the other part also matches with the previous thing. So this is what we want to show, or we want to see that it happens. Now two cases will arise. If n is greater than or equal to m, note that in the original definition, the second recursive part does not exactly have this inequality or this condition, but rather this one. However, the way we have defined our symbol, finite series, it has one definition for n greater than or equal to m. So n equal to m minus 1, that case we have to treat separately. That we will do. Let us first look at this one. Okay, so if n is greater than or equal to m, then summation, let me just do that calculation here on this side. We should really respect, in fact revere the principle of recursive definition and give it its due respect, because it is in fact precisely the thing that got things started in the first place. Without it, we just stopped there itself with the system of natural numbers, with no possible easy way of defining addition, multiplication, those things. And it keeps on providing us with convenient definitions. Then summation ai where I varies from m to n plus 1 is according to us what is this? This is g n plus 1 minus m. Now can we really write this? In order for us to be able to write this, n plus 1 should be greater than or equal to m. But that is all the more true because n itself is greater than or equal to m. So we can write this. Now this gn plus 1 minus m is actually n minus m plus 1. And here we can use this recursive definition. But again, let's look carefully. Can we really use? We can use this if this n is a natural number. That means if n minus m is a natural number. Is that so? Yes, because n is greater than or equal to m, so n minus m is at least 0. It cannot be negative. Now applying that, we have f of n minus m comma g n minus g of n minus m. Now we apply the actual definition of f. The actual definition of f says that it is equal to, note that here the first coordinate of this ordered pair is our natural number and this second coordinate is a real number. So that real number r plus a. Now what will the suffix be? The suffix is this natural number which now plays the role of that n in the original definition of f. So n minus m plus m plus 1, and that is, now in place of g n minus m we can write this. Why? Because n is greater than or equal to m. ai, where I varies from m to n, plus, now this thing becomes an plus 1. So you see that whatever you previously had in our original recursive definition in definition 711, we are again having that same thing. So that means our thing that we have now defined somewhat separately and more rigorously matches with that thing. But there is still one more case. We have to still look at the case where n is equal to m minus 1. If n is equal to m minus 1, okay, then what happens to this sum? N plus 1. You can see that n plus 1 is m, which is a consequence of this equation. So here we have ai m to m. Okay. Now for this symbol still this definition is applicable, because now we have the case where n is equal to m. N and m are the same thing. So that means this is g of m minus m, that is g of 0, and this g of 0 according to our choice is am. Okay, and in place of am we can also write, of course, 0 plus am. Now note that you can write in place of 0 this. Oh, sorry, this is not n minus 1 but n. And what is m? M is n plus 1. Why am I able to write this in place of 0? Because in this case n is strictly less than m, so we are here. So that means 0 is the same thing as this by definition, by our definition. So this is justified, and this am is an plus 1. So in this case also you get that same relation true, it's happening. So that is why, and that just makes everything rigorous. So yes, this new definition, in fact it matches with the old one, but the old one has some little inconsistencies. So we have now addressed that and the issues are over. You can just simply, if you want, you can end this solution with a remark. So this new definition is the rigorous version of the original definition, which matches with whatever we have in the original definition that we want. So now there is no problem with the definition of finite series. Now we go to the actual exercises. And most of them, as you can imagine, are going to be proofs of the theorems we have seen in the section. And that is where the first exercise comes. Seven, one, one. Have you noticed one thing? What happens in any part of mathematics is that when we work with some things for a prolonged period, we get used to them so much that it's easy to miss things. We are very familiar with this symbol. In fact, from an early stage, we have seen these symbols already appearing, and we calculated with these symbols so much that we already have a pretty good idea of what this thing is without going into the intricacies of these definitions. So just looking at this, we are tempted to immediately write AM, but keep in mind that this symbol is the one we have defined in this new definition. So you cannot just simply write AM because I varies from M to M. No, according to our definition, it is G of 0, and that is equal to AM. So that is why it is AM. Okay, so I just wanted to draw your attention to this fact. Now next, prove lemma 714. So that this is the one where we have the basic properties of finite series. There is a hint also. You will need to use induction. But the base case might not necessarily be 0. Yes. Okay, so let us start. So what we will do, you recall that this one had a number of parts. In each part we had one statement, a property of finite series. So what we are going to do is we are going to first of all recall the statements in each part, and then we will prove it. So in part A we had this. Let m less than or equal to n, which is less than p, be integers. Now keep in mind that this of course is not a way of writing a solution. It's just that we want to recall the statements, and that is why we are writing like this. When you write an actual solution, you will just simply start proving the thing because the statement is already there somewhere. So these are integers, and let ai be a real number assigned to each integer I lying between m and p in this way. Then the first part says this thing, that the if you take the sum of these two series, where in one of them the index varies from m to n, and in the other it varies from n plus 1, the next value, to p, then you get this series where the index varies from m to p. Going through these things, something may come on your mind that is there really a point in proving these things which seem very obvious? Yes, there is. You see, these are statements about infinitely many, I should not say infinitely many objects, but these are statements about objects or some things happening in infinitely many cases, because your m and p have infinitely many choices. N also has accordingly infinitely many choices. So what you are saying in this statement actually is a set of equations where there are infinitely many equations. So you know that whatever is written here or whatever is claimed here has been found to be true so far in all the cases that you have come across in your mathematical life where this type of thing occurred. Every time you saw that it is true, but that does not mean that in all the cases it is true. You have to actually rigorously mathematically prove it, then only you can claim it is true. So that's why we are doing this. But we are going to apply now induction. What is the thing on which we will induct? I think some ink will be nice. We apply induction on this variable k, which is n minus m. Are we going to no, I don't think it is p minus n. Okay, p minus m. Note that p minus m is a positive integer because of these inequalities. So on p minus m, on this positive integer, we are going to apply induction. So the smallest possible value of p minus m is 1, and that will form the base case, and that is why the author says, but the base case might not necessarily be 0. It may not start with 0. When p minus m is equal to 1, we have, okay, if p minus m is 1, that means p is m plus 1. So p is just the next integer. We have m here and we have m plus 1 now in this case. So because n lies in between m and m plus 1 in this manner, the only possibility for n is equal to n. So we have n equal to m, and hence, so what happens to our relation now? Let us start with this side. This becomes, because n and m are the same thing, we have this plus okay. Now because n and m are the same thing, we can write m here in place of n, and p is what? P is m plus 1, a I. Now this, by the definition of finite series, is am, and this one is a m plus 1. And that just turns out to be equal to this. These calculations we already saw back when we went through the definition of a finite series, and we saw some of its consequences, initial consequences. So one of them tells us that this is equal to this finite series, which is ai. I varies from m to m plus 1, but m plus 1 is p. So in this case, the left hand side is equal to the right hand side. So that means our claim is true, and this is the base case for our induction. So the result is true for k equal to 1, or when k is equal to 1. Assume that the result is true for some positive integer k. This is our induction hypothesis. Now we have to carry out the induction step, for which we will need the ingredients first. Let m prime p prime be, or okay, let me write like this. Less than or equal to n prime less than p prime b integers such that p prime minus m prime is k plus 1. And we need to consider those real numbers also. Let ai be a real number assigned to each integer I lying between our new m and new p, then okay, now we are going to see the statement for these ingredients, these things. Oh, and here, okay, now here two cases arise. We cannot just directly have everything. If so, one of the cases is this: if n plus 1, we have taken, you can in fact take it to be just n itself, it does not matter. And in fact, if you want, you can write m and p here also. I'm just simply writing m prime and p prime to show that these are any integers, they only satisfy this condition. So if n plus 1 is equal to p prime, okay, then we are looking at what? Summation I varies from m prime to n plus summation ai, where I varies from n plus 1 to p prime, is equal to n plus 1 is p prime, okay, and so this is something we are keeping, or we are changing this one? This is something we are keeping, right? Because we cannot just simply write something else in place of this, not yet. So it just stays like that, and here in place of p prime we can write n plus 1, because that is the case. So this becomes equal to summation ai, where I varies from m prime to n plus a n plus 1, and we know from directly from the definition that this thing is equal to ai as I varies from m prime to n plus 1, which however is equal to, in our present case, this p. Now each step has to be cautiously taken. The fact that we have written this in place of this demands something. It demands that that condition n greater than or equal to m minus 1 be met. Is that happening here? So that means we need this, which is equivalent to n plus 1 being greater than or equal to m prime, but our n plus 1 is p prime, and this is true. In fact, we have strict inequality here. Where is it? E. See? So that means our application of the definition here is justified. So everything has now fallen in place, and in this case we are getting what we want. On the other hand, if so, we have seen this case, n plus 1 is equal to p prime. Now if n plus 1 is less than p prime, why are these the only two cases? That is because we have this inequality. So n plus 1 is either equal to p prime or it is strictly less than p prime. It cannot be greater than p prime. That is because between n and n plus 1 there is no integer. So if n plus 1 is less than p prime, then so again we start with this expression to n plus summation ai varies from n plus 1 to p prime. Now here what we do, we apply the definition in this sense to this second series, keeping the first series intact. So here what we will write, summation ai equal to n plus 1 to p prime minus 1 plus a p prime. The question is again, can we do this? So if you recall the condition, that condition, n is greater than or equal to m minus 1. In this case, the way we have applied that thing here, our n is p prime minus 1, because p prime is p prime minus 1 plus 1, that is n plus 1. So our n here is p prime minus 1. So that means we want this to happen. And our m, what is our m now? Our m now, because we are working only with this series, don't confuse this m with this m prime. In this series, our m is n plus 1. N plus 1. Is this inequality true? Let's see. This is equivalent to p prime minus 1 being greater than or equal to n, or p prime being greater than or equal to n plus 1, and this is true. In fact, in our present case, n plus 1 actually is strictly less than p prime. So writing this plus this in place of this second series is justified by our original definition. Okay. Now all these things look a bit cluttered, but you can make out, I think you can clearly see that this part I equal to n plus 1 belongs to the calculation above, and p prime minus 1 it belongs here. Okay, now you look at this plus this. In its place, I am going to write this. Why and how? This thing is coming from the induction hypothesis. What is our induction hypothesis? The induction hypothesis says that the result is true for some positive integer k. Now, if you look at these integers, m prime p prime minus 1 and n in between m prime and p prime minus 1. Let us see if all the ingredients again are matching or not. M prime is already less than or equal to this n, because that's how we started things. I mean, our m prime, n and p prime, they are coming from here. And do we have this thing? Because if this strict inequality, this particular thing is not true, then we are stuck here itself. But this is true. Why? Because n plus 1 is less than p prime. See? So that is why we do have this thing that we need. Okay. Now originally we had our real numbers ai defined for all integers I lying between m prime and p prime. So in particular we also have those same ai's defined for I lying between in this slightly smaller region, where we are just simply not considering p prime. So for I varying in this range, we still have real numbers ai. What else is true is that, do you see what the difference between this and this integer is? P prime minus 1 minus m prime. P prime minus m prime is what? K plus 1. So p prime minus m prime minus 1 is k. So that means we have whatever we need to apply the induction hypothesis, because that is the thing that is saying that when this difference is k, we can apply the induction hypothesis. And applying the induction hypothesis, we have been able to write this series in place of this plus this. Okay, so that's what we have done here. But the calculation ain't over yet. We still have something else to write. So we have seen that the induction hypothesis can be applied here and everything is okay. Now this is equal to, of course, our ai. Why? Because here again we are using the recursive definition part of our original definition. But again, can we do that? What is our n here? P prime minus 1. Is that greater than or equal to this m prime minus 1? Yes, because p prime is greater than or equal to m prime. In fact, it is strictly greater than m prime. So we can write this thing in place of this using the original definition 711, that recursive part. So now see that we have ended up with that same thing that we wanted to show. Like whatever we had here. Oh, I wrote p, no? This will be p prime. That this plus this is equal to this. Here also, this plus this, same thing, is equal to this. So this completes the induction. Once you prove these things and once you verify that everything that we are familiar with is actually true, then you can just simply, dare I say, forget the actual definition and continue working with these things as you have always been working. Completes the induction, and hence it completes the proof also. Then that is only part A. Now next part B. The statement of part B is this: let m less than or equal to n be integers and let k be any integer. Then this part claims, oh okay, we need the AIs also, no? Let AI be a real number assigned to each integer I lying between m and n in this way. Then summation AI, where I varies from m to n, can also be written like this: a j minus k, where j varies from m plus k to n plus k. Now while going through this section, when we wrote all these things down, that is when we stated the theorem properly, that time we did not go through these statements very minutely, or we did not try to see actually what they are saying. But do you see one thing? There is no problem with the first series. The second series, however, in that we need to make sure of something. You see, we are talking about a j minus k. Do we have these things? I mean, AI is defined only for these values of I. Now what about j minus k? You see here j lies between m plus k and n plus k. So that means so if you subtract k from all the terms, then you get these equivalent inequalities. Oh, sorry, this is j. So j minus k in fact is just like I. So these a j minus k's are nothing but the original AIs, and that is why you can clearly see this thing is equal to this. But that you can clearly see is a vague way of justifying that this is true. We need to prove it. Again by induction, we apply induction on, you can pretty much guess what that will be. N minus m. Note that n minus m is a non-negative integer because n is greater than or equal to m, or in other words it's a natural number. So in this case the base case will be 0. So let us start our argument. When n is equal to m, that is when n minus m is 0, we have summation ai varying from m to n varying from m to n, which we know is nothing but am. Now this am can be also written like this: a m plus k and minus k. Okay, m plus k minus k, which is the sum of this series. Because here also the lower limit and the upper limit of this series are the same. If you can call them, right, these names, lower limit and upper limit. So the way we have defined finite series, this thing becomes equal to only a single term where that j takes that thing, that common limit. But now because again n and m are the same thing, so we get this. So we are getting what we want. So the result is true when n is equal to m. Assume that the result is true for n minus m equal to say r, where r is some natural number. So this is our induction hypothesis. Now in order to carry out the induction step, we will again need the ingredients. So we assume them let oh, we forgot to mention one thing now. We did not mention anything about k, that integer k here. Do we need to? No, we don't need to. What we are assuming here is that the statement is true for n, m and k, where n, m and k are any integers. The only restrictions are n is greater than or equal to m, and in fact n minus m is equal to r. K is any integer and the ai's are any real numbers where I varies from m to n. Okay. Here, however, we need to take a k. So let n prime, m prime and k prime be integers such that n which one was smaller? M was smaller, of course. M prime is less than or equal to n prime. Also, let ai, if you want to keep this practice of writing different things in the induction step, then ideally you should also write ai prime, but I am not doing that. Okay, in order to not be needlessly artificial like this, let ai be a real number assigned to each integer I lying between m prime and n prime. Oh, I should have mentioned that thing here itself, that the difference between n prime and m prime excuse me, and this thing is r plus 1, because otherwise it won't be the induction step, it won't lead to the induction step. Let ai be a real number assigned to each integer I lying between m prime and n prime. Yeah, now we have all the ingredients. Now we are ready to cook the meal. Then summation ai, where I is now varying from m prime to n prime, is equal to again like before m prime n prime minus 1 plus a n prime. Again that question arises, can we really do this? Let us see. N prime, for us to be able to do this n prime minus 1 should be greater than or equal to m prime minus 1. which is true because n prime is greater than or equal to m prime. Now look at this series. Here the lower limit is m prime, the upper limit is n prime, and shall we have cases here also? Let me see what I did here. No, luckily we won't have cases here. What I was thinking is I of course want to apply the induction hypothesis to write this series separately, the one involving j, k and all those things. But my concern is, can I do that? We want this to happen for us to do that. That means equivalently we want this. But this will happen because this is what? R plus 1. R is some natural number, so R is the least value of R is 0. In any case, this is greater than or equal to 1. So yes, we can apply the induction hypothesis. And doing that, we have summation. Oh, and one more thing, we are being able to apply the induction hypothesis here. Why? Because this minus m prime is R. That is why, which is coming from this one, of course. So using the induction hypothesis, we can write this series as a j minus, being somewhat careful, this time we are writing k prime because that's what we have taken, and here j varies from m prime plus k prime to n prime minus 1 plus k prime, okay, plus in place of a n prime we can write a n prime plus k prime minus k prime, okay. Now can I write in place of this, using our definition of finite series and its recursive relation, this thing, to n prime plus k. Can I do this? I can do that provided I have this inequality, n prime minus 1 plus k prime, it becomes greater than or equal to the lower limit minus 1, that is m prime plus k prime minus 1. Now you can see that this requirement, this condition is equivalent, because we have k prime minus 1 on both sides, it is equivalent to just this, which is true. Or I mean, we have that from here, so we can write this one. and that just completes the induction. Because in this new setup also, where we have m prime and n prime, we have been able to write this series as this one, which involves that j, and this one will be k prime. This completes the induction. I will prove one more and leave the remaining three to you, because their proofs are similar, very similar, and in fact much easier than this. In fact, this very next one is, the statement is much easier than this. That is because here you are subtracting k prime from the index, you are adding here k prime to the lower and upper limit to compensate for that. It is a little complicated, but the next one will not have those complications. This completes the induction. Now part C. Part C involves two sets of real numbers, ai and bi. Let m less than or equal to n be integers. Let ai, bi be real numbers assigned to each integer I lying between m and n. Then summation ai plus bi is equal to summation ai plus summation bi. And this clearly happens because addition of real numbers is associative, it is commutative. Because of those things it happens. So we now prove it. Again, like before, we apply induction on n minus m. And n minus m, of course, is a natural number. Everything is just like b. So when we next look at the base case, which is when n is equal to m, that is n minus m is 0. When n is equal to m, summation ai plus bi, where I varies from m to n, is this, which by properties of finite series, or which come directly from the definition, is am plus bm. there is only one term in this series, and am just like that because of that same reason equal to this series value, and bm is this series value. N. So our statement, our claim is true. So the result is true for n equal to n. Assume that the result is true. Some people will find it a little uncomfortable to write result because something does not become a result unless you prove it. So if you feel like that, you can write claim in place of result is true for any integers n and m such that n minus m is equal to r, where r is some natural number. Note that unlike usual direct induction in which you just simply deal with one natural number or one integer, actually there are two integers here. So that is why if you look at this induction hypothesis closely, you will see that this hypothesis is not about some arbitrarily fixed n and m. Some arbitrarily fixed r, of course, where r is some natural number, but n and m can change. For example, if your r is 1, n can be 3, m can be 2, n can be 4, m can be 3. Like that, there are infinitely many choices for n and m, and we are assuming that for all such choices where the difference is 1, this statement is true. So the induction hypothesis has a lot in it. Now let n prime comma m prime be integers such that n prime minus n prime is now r plus 1. Let ai bi be real numbers. If you are wondering about one more thing, we haven't said here anywhere that n prime is greater than or equal to m prime. That thing is a consequence of this because r is a natural number. So in this case particularly, in fact n prime is strictly greater than m prime. This be real numbers assigned to each integer I lying between m prime and n prime. Then summation ai plus bi, where I varies from m prime to n prime, is equal to the rest of the proofs we are not going to do, because by now you are, I hope you are realizing that there is a sameness to these proofs. You reduce the series to the lower stage by taking one term out, and then to that reduced series you apply the induction hypothesis. That is basically the idea with all these proofs. Bi plus an prime plus bn prime. Also make sure that you can do that actually. This must be greater than or equal to the lower limit minus 1, which is okay, and it is true because we have this n prime is greater than or equal to m prime. In fact, it is strictly greater than m prime. Okay. Now this is where you can apply the induction hypothesis. Why? Because here the upper limit minus lower limit is equal to r, and that is the case where you can apply the induction hypothesis. So that thing that I was saying just now, that there are many values of n and m for which which are parts of the induction hypothesis. One such pair is n prime minus 1 and m prime, because their difference is r. So in that case also we have our statement, and that statement is this: n prime minus 1 plus minus 1 plus an prime plus bn prime. Now you can imagine what you have to write in the next step. You just have to move the an prime closer to the a series and bn prime closer to the b series, and then again apply the definition of finite series, and you have your result. That is, this thing is equal to summation ai plus an prime. This is one thing, and then bi bn prime. This is the other thing. So if you now again apply the definition of finite series, its recursive part, then you finally have what you want. So this completes the current induction and proves this part C. And the other parts, I won't leave it like this. I will just simply mention. The other parts I leave completely to you. I am not going to do them. One can similarly prove parts D, E and F, and this completes the proof of our original proposition. So now we know that all the basic properties of finite series, which we have been using for a long time. The moment we learned about finite series, from that time itself we have been using these things. So we can now use them with the certainty that all of them are true, and the basic properties of finite series are now available to us with the assurance that yes, it has been proved, so it will always be true, despite the fact that there are infinitely many cases where this thing is true. That's what we have proved. So I'm ending the video here itself. We will solve the other exercises which come after this in the next analysis video. So today is Sunday, tomorrow there is no video. On Tuesday we again go back to graph theory, where we will see graph minors and something else also. I think we will see what comes up. So that being said, if you want to say something about these things, you can write in the comment section below, or you can mail me at my address, which will be there in the description. You can find the link there. And that's just it. So on Tuesday we are again coming back with graph theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.